Hello everyone. Um, am I audible?
Yes, you are right.
Okay, fine. So now I will start sharing my screen. So, okay. So I hope the slide is visible to you all. Is it visible?
Yes.
Okay, fine. So, okay. So now let's start. So good evening, everyone. Welcome you all to the week 5 of doubt and problem solving session. Sorry, sir. So week 5 of doubt and problem solving session of techniques of material characterization. So I believe that till now, whatever the session we are covering and that are going to help you to solve your assignments in a more efficient manner. So similarly, pattern will follow in this week also, and we'll try to take some questions which are related or to week 5 lecture modules, and that will that will help to solve your assignment number 5. That will help to solve you the assignment number 5, and we'll begin with the questions now. Okay, so before starting this all the problem solving sessions, I believe and I hope that you all have seen your uh, assignment number 5 questions and the pattern. So it will be also somewhere somewhat related to your assignments question only, and I'm also expecting the same, that you all have seen the lectures also, if not all, then at least a few lectures, so that you will be able to answer the questions when I will show you the questions here. So let's begin the discussion. So we'll firstly start with our first question, which is related to the diffraction pattern. So here this question is asking diffraction pattern in an electron diffraction for a crystalline material. So remember, this is asking about the crystalline material. So the option is similar to light diffraction. Intensity decreases monotonously with increase in scattering angle. Intensity increases monotonously with increase in scattering angle. There is diffuse local intensity maximum at certain scattering angle. So when the electron is coming and when there will be the electron diffraction in any crystalline material, then how this from the given options, how your intensity is changing it with respect to the scattering angles. So if you have gone through the lectures, then probably you would probably try to give the answer for this question. So anybody knows this?
D.
D. Okay, so okay, fine. D. So why you are saying D, and what is the reason? Why not the other options? Or any anyone else wanted to say something regarding the answers or the reasoning behind this question? So they can also answer. Okay, fine. So we'll see that how this will go, and here it is like this. So suppose in the slide you can see this is your specimen of thickness T, and the beam is coming, and this is your diffracted beam, and this is your direct beam. Okay. So here it is giving some relation about your intensity. So the here the intensity of scattering from the crystal. So this will be for this pattern or for this arrangement, when the electron beam will come. So it will obtain by summing the scattering from each slice. So suppose this is thickness T, so you can assume of the slice of this specimen, taking into account phase difference of the waves scattered at different depths. Okay, so here you can see there are the electron beam is coming, and this is scattered at different depths. So here the first one is this is the diffracted beam from the different depths. Okay, so here the intensity will be related to this equation. So where this is T is the thickness, and this is the function of this parameter. So here you can see the intensity plot. Okay, here you can also you can see that the variation of the diffracted intensity, okay, with the deviation from Bragg angle for the specimen thickness. So here you can follow this deviation from the Bragg angle. So here this will be the intensity, okay, where the electron beam is coming. And when you if you have gone through the lecture of the reciprocal lattice, so I believe that you have you know the reciprocal lattice and the evolved sphere also, which I will be going to talk in this lecture also. But for this question, if you have to know, so here the intensity is at higher, but when you go to the plus and minus s, the intensity will be going to decrease. Okay, so it is slightly going to diffuse. So here it is asking about, okay, intensity increase monotonously with it increase in scattering angle. So but here there is a diffuse in the local intensity maximum at certain scattering angle. Okay, so where Bragg's angle sorry for the diffraction to be happened, it should follow the it should satisfy the Bragg's law. Okay, so here it point where it will where it will satisfy the Bragg's law, it will give the maximum intensity, and where there you will find the diffracted spot. So here, but when you go to the other sides, you will get the diffuse or lower the intensity. Okay, so answer D is correct. So here from this slide you can see, and also you want the further detailed discussion also, then you can see this whole lecture, you will get a better understanding regarding this, but this will be the main part. Also, for the diffraction to be happened, so your this will be, suppose your reciprocal lattice, so your reciprocal lattice should touch your evolved sphere. So till now we have seen only that to diffraction to be happen, you need to satisfy the Bragg's law, but apart from this also there will be the condition that the diffraction will occur, and you can see the diffracted spot only when the evolved sphere will touch the reciprocal lattice. Okay, so here you can see the real crystal. This condition can be relaxed, resulting in significant diffracted intensity. So here you can also see that the difference in the diffracted intensity. So this is related to the touching of your evolved sphere with your diffracted spot. So also we will see in the further slide that how this intensity and the diffracted spot size is changing with respect to the thickness of the material. So here crystal which is not oriented exactly at the Bragg's angle, so reflecting sphere missing the reciprocal lattice point by a vector s. So here in the last slide we saw that the intensity is maximum, and this side will be the plus s, and this will be the minus s. So s will be the vector. So here there would be no diffraction under this condition, because diffraction only occurs when the reflecting sphere touches reflecting is sphere. It means the evolved sphere will touch the reciprocal lattice, then only the diffraction will occur. Okay, so from the like last slide I saw shown you that there is a diffuse local intensity and the maximum at certain scattering angle. So this will be the right answer. So as I discussed you in the previous slide, and I said you that the what will be the effect of the thickness of the material for the diffraction spot size. Okay, so here this question is regarding that, and here it is asking if the specimen is thinner, the diffraction spot size will be what, and you have to give the answer that how it is changing with respect how the spot size of diffracted spot size is changing with respect to the thickness of the material. Okay, so if the specimen is thinner, then what will be the diffracted spot size? Whether it is larger, it will be smaller, and will be the same, and it will disappear. So can anybody answer?
Answer A.
Why?
Thinner the crystal size, then the crystal may deviate from the back condition, right? So that relaxation of the evolved sphere will be high from that.
Okay. Anybody else? So I believe that people are seeing the lectures, and because here this session is not just about to solving your assignments, because if you will not put your effort, then probably it will be very difficult for me also to know you better. Okay, so it is not just regarding the showing you the questions and the slides and giving you the answers. It is more about the discussions. So if you will participate more, then for the next for the next lectures it will be more, enthusiasm for me to prepare more and more content, and I can discuss more. So I hope that you guys will participate and give your opinion, and it doesn't matter that whether it is wrong or right. We are not here to judge for your answers. It is just a simple discussion, or you can give some logic. This is how you can learn better and more efficient. Okay, so just think about this, so that if you will not even take the interest, then it will be for me also, it will be very easy to just prepare the questions and the slide and give the answers. So I hope you guys understand this. So okay, let's come to the questions. So it is regarding the thickness of the material to the diffracted spot size. So here, when you will see, okay, so this is in the below diagram, where you can see many diffracted spot, and you will be able to see the change difference, okay, in the spot size. So here you can see more clearly, okay, but here when you will thickness is increasing, suppose here for the A, the material is very thin, and when you will be increasing the thickness of the material, how your diffracted spot size is changing. Okay, here you can see the more clearly, but here you can't see, and the size is also changing. Okay, so here, as I said that for the diffraction to be happened, the evolved sphere should touch the reciprocal lattice. So here, when your material will be the thin, and the thinner the crystal, the further the crystal may deviate from the break condition. Okay, and that will lead to the diffraction. So here, when you will construct the evolved sphere, then there will be the relaxation of the diffraction condition for a thin crystal. Okay, and this will lead in a way that the reciprocal lattice points are now extended in a direction normal. So suppose this will be your beam is coming. Okay, so here it will be the direction normal to the plane. Suppose this will be the plane, so here it will be the normal to the plane of the specimen. Okay, so since you for the if your material is thin, then you can assume then this sphere will be in a shape that it will touch the maximum reciprocal lattice, and it will be in the shape of your, sorry, it will be in the shape of your rod, or even in the 3D it will be in the shape of your cylinder or the cylindrical. So since if you will assume like this, then the length of the rod is inversely proportional to the specimen thickness. Okay, so if your material or your specimen is thinner, then you will be able to get the more diffracted spots. So I hope some peoples are coming very, very early. Okay, so since the length of the rod is inversely proportional, sorry, so here we are assuming the rod. Okay, so it will be inversely proportional to the specimen thickness, and if your material is thinner, then this rod will be able to touch more and more diffracted spot. Okay, so when your material or the specimen is thin, you will get the more intensity, okay, as well as the more diffracted spots. Here you can see in the figure A, the number of diffracted spot is more because it is thinner. When you will be go from the lower thickness to the higher thickness, the number of diffracted spot is reducing. Okay, fine. So here the answer will be, the specimen will be thinner, then the more will be the larger the larger the large will be the number of the or the larger will be the size of the diffracted spot. So earlier the question was related to the size of the diffraction spot. Here it is the related same that I have answered the same also in the last slide. The number of the diffraction spot. Okay. So again, I believe that this will be also the same. Here thinner will be the material, more will be the diffraction spot. Thicker will be the material, less will be the diffraction spot. So here it is asking, in electron diffraction, a greater number of diffraction spot appear for thicker, thinner, or these are two other answers. So here, when your material will be the thinner, more will be the number of your diffraction spot. Okay, so this question is related to the orientation of a crystal. Okay, so there is some arrangements in your TM. So it is asking which will be the least accurate method in determining the orientation of a crystal. Okay, in nanometer range. So if you have gone through the lectures, you will probably know that what are the arrangements and some pattern that will evolve in order to get the orientation of a crystal. So can you guys guess? So there are 20 people.
For orientation, selected area diffraction is the best one. No?
Okay, so why you believe so? I mean, what what is something that is lead your SAD pattern to give you a orientation of a crystal? Okay. Does anybody know that what is SAD? That I have also talked about this probably in the last or the maybe I do not remember, but in some lectures. What is selected area diffraction pattern, and what is the use of this SAD pattern? Why we need this?
Through ACD, we can filter out the unwanted rays, and we can mainly focus the whichever the beams that it is focused on the given interested area. For example, because some heterogeneous samples are there. If I need to go for the specific area, then this type of this pattern is helpful. This mode of operation.
Okay. Apart from this, anything else? Because for that also we can in optical microscopy in SEM we can use some lenses, some electromagnetic lenses. Then why only this is required in this?
There we cannot go for higher magnification where you can go up to the atomic level.
Okay. Okay, fine. So I will also talk about this when I will show you the arrangements in some slides. So here it is asking when you will be using the SAD. So here there is some arrangement of which is called the SAD. So there will be some holes. Okay, so it depends upon what is the size of your crystal and the grains, whatever it may be in your samples. So there will be some aperture and there you will have some holes. Okay, so through that holes your beam will go. So if your crystallite is very smaller, you need to use a smaller aperture size. Okay, so that will also lead. I mean that is also somewhere related to the intensity because you need some intensity in order to see the atoms or you in order to see the crystals. Okay, so it is asking about the orientation of the crystal. So here suppose this is a pattern diffraction pattern of a titanium, aluminum and the vanadium alloy. This is a two-phase alloy. So here you will have a alpha and the beta phase. So here you will have a alpha and the beta phase. So alpha will be here, you can see the zonal axis of the alpha is given. So here by the number itself you can guess that it is HCP, hexagonal close packed, and the beta phase is your body centered. So if you will go through the lectures then you will be able to know that how it is determined. Okay, there is some rules and I will also show you, and I have also included that in some slide. So here uh, SAD can be used to identify the crystal structure. Okay, and that will because here you can see because here if you by using the SAD aperture you will be able to you will be able to see the more diffracted spot. Okay, so if you can see the more diffracted spot, probably you will be able to find out the crystal or the orientation of the crystal. Here you can see this is 2 bar 1, okay, 200, or some 1211. Okay, so here you can see that how this is arranging. So this will be only possible when you will be using some aperture, then only you will be able to get some focus beam to get this kind of a diffracted spot. So okay, so this is also pretty much similar to the XRD, but here the difference is here when the area is smaller to the in a nanometer range. In a nanometer range, then uh, okay, so here 100 nanometer in size can be examined by using this SID aperture. So here probably you will be able to find the arrangement of your crystals or the atoms in order to find out the orientation. So for this you need to know the many factors like your zonal axis and your HKL, then only you will be able to solve this in order to know the orientation of your crystal. Okay, so the answer will be your SAD pattern. So if you have seen the lectures, then there will be some diffraction pattern. So like in this is also depends on your material, whether your material is a polycrystalline material or the single crystalline material. Okay, so if there is a change in the crystalline of your material, there will be change in the diffraction pattern also. Okay, suppose I have shown you that, okay, this answer will be your there will be, you can see some spot size or the spot pattern, spotty pattern. There is a ring pattern, streak pattern. Okay, so here when you will be using the polycrystalline material, then probably you can see here some ring kind of a pattern is occurring. Okay, so in the polycrystalline material, suppose this is a different crystallite. Okay, these are represented by the different color. So the main reason of getting this ring kind of a pattern is a superimposing. Here the diffraction pattern of the different crystal will get superimposed. Then that's why you will here get in the polycrystalline material some ring kind of a structure, because here if it is a single crystalline material, then the diffracted beam will come, and if it will your evolved sphere will touch the reciprocal lattice and it will satisfy the Bragg's law, then you will get some spot. But here since your there is a superimposement of your different crystals, then the diffraction will occur from the each crystal. Okay, so since the d value and the distance in reciprocal space are the same, the spots are then located on rings. So it will create this kind of a pattern which will be like a ring. So here you can see this is for 111002 and like that. Okay, so here the ring diffraction pattern from a polycrystalline pure gold film with FCC crystal is shown here. This is the value of the spacing d. So here for the single crystalline, so here you can see the single crystalline material, you will get this kind of a spot. But when you will go from the single crystalline to the polycrystalline, you will be getting this kind of a ring pattern for the diffraction. Okay, so here single crystal diffraction, it will be arranged event in which the crystal and the X-ray beam must be configured so that the Bragg's law can satisfy, which I already said, and that's why the diffraction will occur. For the diffraction to be occurred, the Bragg's law should satisfy. So here, if this is not satisfied, the crystal must be rotated so that the angle theta becomes equal to the given by Bragg's law, and then only the diffraction will occur. So here the more which you need to know is about the superimposement. So different crystal will superimpose and the diffraction will occur from there. So that's why it will create a ring kind of a pattern. But here since there is a no different crystals, so you will get a spot size in the diffraction. So you will get for the polycrystalline, remember this, you will get a ring pattern. Okay, so a diffraction pattern cannot provide information about what. So since last week 4 we are seeing about the diffraction pattern. So it is what the information we can't get from the diffraction pattern, and it is very easy. We are seeing in the different lecture, we are talking about the orientation, some crystals, some spacing, and all many more. So can anybody guess that or have some answer for this question?
Elemental composition.
Okay, so do you know from what we can get the elemental composition that I have said in some lectures, maybe in week 4 also? What do you require
ED,
for the elemental composition?
EDS.
Hmm. Right, correct. Okay, so for the elemental composition, in order to know the elemental composition, you need to have some spectroscopy. So for an example, in SEM we have a energy dispersive spectroscopy. Okay, so from there we can say about some elemental composition. But here in the lectures also, if you will see, you won't get any kind of a discussion which is related to the composition. So okay, so here you can see what is the importation of in the slide of indexing of a diffraction pattern. So what are the information that you will get from here? So you can measure the camera constant using polycrystalline foil. You can get the diffraction contrast mode. You can identify the unknown material. How? From the lattice parameters and the symmetry, you need to know the lattice parameter HKL. So suppose here for the aluminum or for the FCC crystal, what will be your this lattice parameters, and what is your symmetry? You need to know the symmetry also. To measure the you can measure the interplanar spacing of a material, and determine the exact orientation of a material, determine the habit plane and the epitaxy or orientation relationship. Okay, so this you will be seeing in the last slide about the disk location in this TEM. So to produce the defect contrast, okay, so this will be your line vector and the Berger vector should be contrast, and to determine dislocation Berger vector. So these are some information that we can get from the diffraction pattern, but here it is not discussing about any composition. It will just on the basis of your crystal. Okay, whether it could be for any material, any composition, it can be any material, whether it is a aluminum copper, whether it is a gold, or whether it is a titanium aluminum vanadium. It could be anything, but it is related to your crystals. So the elemental composition is something that we can't identify from the diffraction pattern. So which one is incorrect? Transmitted electron from bright field TM image, scattered electron from a dark field TM image, diffracted electron from bright field TM image, and this B and C. So what do you think that which one will be the wrong?
Answer A.
Okay, answer A.
Sorry, yeah, for transmitted, it's a bright field, right? It is right. Okay. For dark field, we need a direct light. Answer B, the wrong answer. For dark field TEM image, you need to give the direct beam. For that purpose, diffracted electrons need not necessary. So the answer is B.
B. Okay. So here in the slide you will see the dark field imaging in TM, which because this is just asking about which one is incorrect. Okay, so you can see the probably transmitted electron that in the previous lectures you have seen in the bright field TM image, and you can see the diffracted electron, sorry, the scattered or the diffracted electron from a dark field image in TM image. Here you can see how it will goes. It is for the dark field imaging in TM. So here there are some patterns. Okay, so you will get some diffraction pattern. So this is for the single crystal specimen you will put here, and you will have some arrangements. So uh, here the signal from a diffracted beam, a dark field image you can receive from the TM. Okay, but I don't have I haven't seen the diffracted electron from bright field TM image. So I think so, because we have seen this transmitted electrons which I have shown you in the previous lectures, and also the diffracted electron you can see from here imaging in TM, but there is no diffracted electron you can't see, or from your bright field TM image. Okay, you can see the dark field TM image. So the diffracted C will be the answer, the diffracted electron from bright field image. Okay, this you can't see, bright field
But for
TM.
bright field, we can't see. For farming, we need a direct beam, na? Direct
Yes,
electron.
yes,
Okay,
this is
okay,
for the dark field imaging. You can
yes.
see the TM image for the dark field, but not for the bright field. If you will be using the it is not asking about the transmitted electrons. It is asking about the diffracted electrons. So don't be confused about the transmitted electron and the diffracted electron. In case of the bright field TM image, if you will use the transmitted electron, it is correct answer. But if in case of diffracted electron for the same bright field TM image, you can't get the diffracted electron. You won't get the image. So this is this. Okay, so this will be your incorrect. Okay, so it is asking about the choose the wrong one. SAD pattern is used to just now I have discussed about your SAD pattern. So is used to accurately determine phase, orientation of phase with respect to electron beam, lattice parameter, none of the above. So what is there that is used to accurately determine? So it is asking about the wrong one. Don't select the right one. So just tell me about the opposite, that what we can determine from the HID pattern. Just I have shown you some slides with the diffracted spot.
We can show the orientation. We can show
Orientation we can show. What else?
phase also, na, whether it is a single phase or phase also we can.
Okay. And can we get the lattice parameter?
I don't think so. I need to again refresh it.
Okay. So first thing is the if you will see this slide, face identification from SAD. Okay, you will, if you will have a lattice parameter and the day spacing, you can identify the face. Okay, when you will go through this lecture, then how you will be get more understanding. And I'm believing that since that nobody is answering that, I don't know how, why you are not answering, but if you will see the lectures, probably you will have the more interest, because if you won't see the lectures, it will become little tedious. Okay, but it is not that tedious. You just need to know, or you should know the little bit behind this crystallographic things. So you can also for the basic, if some students are facing problem, they can prefer a very basic book which is called the this WD Callister. So of the your introduction to material science. So there you will have some basic information about this FCC, BCC, and some lattice parameter, and symmetry, and your all the crystallographic related to concepts you can get from there. So if you are facing, or if you're not understanding this in this lecture, then I will recommend you that book. It is online available also, and you can also get the book from your college and the library, so it will be easier for you to understand this. So here face you can see from the and the orientation, as somebody has said that we can also determine the orientation from the electron diffraction. Here if you will know the zonal axis, if you will know the HKL and the u will w, then and if there are some patterns, you can get the diffracted spot size, then you can know the orientation of your crystal. Okay, you will you can get this, what is the orientation, this is the angle. So but here the none of the above is your answer, because here you can also get the lattice parameter by this
But
distance.
from lattice parameter, are we calculating from d spacing?
Here it is saying HKL. Yeah, no, there is some there is the formula na. So for the what to say this, if you will know this d spacing, okay, if you know the everything, then there is one slide the formula. From there you can get the lattice parameter. So for the different crystals, do you remember the formula regarding that? Maybe I forgot to include that in the slide, but there is some
Yeah,
formula which is
I
related
know
to the.
FCC 4R is equal to root 3.
Exactly. Yeah, yeah, yeah. That one I'm saying. So from that you
Then I
can.
can calculate according to that, we can calculate EA. That's right.
Yes. So this is, so once you know the crystal of your, the crystal of your specimen or your material, what is the crystal? Then suppose if it's a FCC crystal or the BCC or the simple cubic, you will be able to get the HKL, sorry, this lattice parameter, which is usually in the formula it is given by the A. So from there you can get the lattice parameter. So from the SAD pattern you can get the everything. So the none of the above will be your answer. So here it is a very small numerical question, and very quick. If you have mobile in front of you, just answer this. It won't take too much time. So this is if you have known the evolved sphere. I am talking since the first slide about the to get the diffracted spots, the lattice reciprocal lattice need to touch the evolved sphere. So here it is giving the radius of your evolved sphere, which is 300 per nanometer. So what will be the operating electron wavelength of that instrument? So please give answer. This I need the answer from everyone, whether it is wrong or right, doesn't matter. Just, or if not, then just type in the chat box. I will see from there. Okay, somebody is asking the book name. So it is
0.33. Whether
how
you
have
are,
you calculated?
that is inversely proportional. Radius is inversely proportional to the wavelength. From that we
Okay,
can calculate. If I know the lambda, then it
okay,
is inversely proportional. 1 by lambda it will become. According
okay,
to the formula, L lambda is equal to RD from that.
okay. So I have written the name. Somebody was asking. So it is Introduction to Material Science by W.D. Callister. So it is online also available. I have some, I don't know, but I had the book when I was in my BTech. So it is available online. You can easily get. So okay. So other people, could you please answer that? What is your answer? What did you get? Please type in the chat box if you are not willing to answer. I am seeing. You just see the question again. It is asking about the wavelength, and only one parameter is giving, which is the radius of the evolved sphere, which is 300 nanometer. So what will be the wavelength? Just calculate that. It is very simple formula, very simple. Just like one person already said this. So other also please answer this. So somebody is asking. Okay, so I will give the formula also. So the radius is giving. Okay, so you just do the 1 by r. Okay, so somebody wrote 0.033. Okay, 0.033, but you missed something, 10 you have missed, and that is also, you just calculate it again. There should be 0.0033.
Yes, he's mentioning in angstrom, boss. We need to convert into nano, then it will become 0.003 because you are given in nanometers.
Yeah, right. You are right. No, where it is asking about the angstrom, here it is
That's
not
why
saying.
he confused. Actually, we
So
need to
it's
convert
it's
it into nanometer, na?
it's fine. Even if it is giving in nanometer, you can give the, even if it is, for an example, if it is asking in angstrom, here it has not mentioned anything about this, so you can give the in nanometer only. So if in your assignments question or somewhere else, if it is asking about uh, in angstrom, then you will probably have to change the parameter or the unit. But here it is fine if you can give the in nanometer. Just do the 1 by r, you will get the answer.
Yes, we have done.
Okay. So I will also show you the slides if somebody is confusing that where they will get. So this will be your evolved sphere. This is your reciprocal lattice. So here you can see this will be the radius of your evolved sphere. So evolved sphere of radius 1 by lambda is drawn. So the radius is given by 1 by lambda. So r is equal to 1 by lambda. So lambda is equals to 1 by r. Right. So just you need to do the 1 by r and you will get the answer. So answer will be 0.033 or 34. You can write, it is acceptable. Okay. So as per structure factor, forbidden reflection for FCC crystal is what?
220.
220. Why 220?
For satisfying the BCC, for satisfying the FCC,
Hmm.
the given parameter should be all even or maybe the odd. For
Okay.
example, for BCC, the sum of them should be even.
Are you missing something in the question? There is also something called a forbidden reflection. So just
Oh,
think.
okay, I see. Okay.
Okay, fine. So I will show you some which I got. When you will do just Google search and there will be the different unit cell type. There will be the allowed reflection and the forbidden reflection. So for the FCC, okay, it
Understood.
should be HKL mixed odd even. You got it? What you were saying was that the HKL should be all odd or all even for the FCC. But here for the, this is for the reflection to
Allowed
be allowed.
reflection.
But
Yes,
for
yes.
the forbidden reflection, it should be mixed odd even. So from here you can see this is all odd, this is all odd, this is, sorry, this is all even, this is all even, this is all odd. So what you can see which is mixed? Huh?
0, 0.
Sir,
What?
100.
100. Right. No. Okay, yeah. So, right. So here for the forbidden, they should be mixed. So you just remember this thing. Okay, it can be asked in your assignments about the BCC or some SCP or anything else. So here it is asking, since asking about the FCC, it should be mixed odd even. You
Yes.
can
In
also
our
get,
assignment, in our assignment is allowed reflection. Yes, that's why I was a little.
okay, allowed. So that's why I said you that
Yes, yes.
be conscious about this. Just go, don't go, just by seeing the question. You need to read the questions very well. So here in this slide also, there are some talk about the forbidden reflection, so you will get some information, but I won't go much in detail that how you are getting this all. Maybe most probably if you will see this lecture, you will get that how for if you will use the FCC crystal structure, then what will be their interplanetary spacing, what you will get first 111, then 200, then 220, then 311, and how and why. But for this question, I showed you the answer. Okay, so for a high energy electron beam, the radius of evolved sphere and the diffraction angle respectively are large and small, small and small, small and large. Say something. You can write in the chat box also. It's no problem.
Can you show the question boss? Once again?
Yeah, sure. So here it is asking about if you are using a high energy electron beam, then what will be the radius of the evolved sphere and the diffraction angle? Then it is asking the relation of your r and the theta. Just think about the slide which I shown you for the evolved sphere.
Small and large. Uh, D answer.
D answer. Okay.
Yes.
So I will show you the same slide again. This is your evolved sphere. Okay. So just think if you increase. Okay. So just think like this. So here 1 by lambda is what? Your radius. Okay. So if you will increase the radius. Okay. So suppose here the angle is theta. This is your scattering angle and this is your radius. So in this lecture you will get that how this evolved sphere will construct. So here when the radius of evolved sphere is large, okay, so then you just think if you will increase the radius, then your this theta will get smaller and smaller, it will come closer, okay, in the reciprocal lattice, because this you will get to know in the lecture that how this will construct. But when you will decrease the radius of your evolved sphere, this theta angle will go like this, increasing. So if the here this is asking about using an electron beam of 100 kilo electron volt, then you will get, since this is also a high energy electron beam, you will get a large radius of your evolved sphere, but the scattering angle will be the small. From this relation also you can get, but here just think about that. So high energy electron beam, your radius of your evolved sphere will be large and it is inversely proportional to your diffraction angle, so this will be your smaller.
Yes. Sorry. Yeah.
Okay, so this will be your large and small. So Berger vectors of dislocation can be determined in TEM by what? Do you know what is Berger vector?
Yes. The magnitude of the dislocation. How much magnitude the dislocation?
So others who don't have the knowledge, they can recommend some book for this Berger vector or the dislocation. You can see again. You can get this for the basics in this WD Callister, or
And
you can
dieter also.
Dieter also. You can get the mechanical metallurgy by George Dieter. I forgot the spelling, but it is something like this, or what you can just check. So yeah. So there you will get good information about this Berger vector and the dislocation. So here the Berger vector of dislocation can be determined in Tm. So here, okay, there will be the dislocation, two types of dislocation, edge dislocation and the screw dislocation. It is showing this positive edge dislocation. Okay, so here this will be your beam. So here you can just see it is, so the dislocations are invisible or exhibit only weak contrast if this, your line vector and the Berger vector will be zero. So the dislocation will appear. Here it is also saying about the dark line in the bright field image, but it is not related to that. So here it is somewhere related to, here the line is coming. So since there is a tilt in the plane, so here your diffracted beam, instead of this, it should go like this. But here, due to the change in the orientation of your plane in the axis, your diffraction beam will go like this. Okay, here you can also see for the different Berger vector. Here this is 1 bar 1 1. This is the same family, 1 bar 1 1 bar. So here this is about the dislocation contrast here, but how you will get, so this is respect to the zonal axis. So in the previous lecture I showed you, I have also given you some numerical regarding the zonal axis. So if you will change the zonal axis, you will get the different orientation. Okay, so by changing the zonal axis, or if you will select a different zonal axis, the Berger vectors of dislocation can approximately determined by this. Okay, so others you can't, like SAD pattern. SAD pattern is just related to your, intensity and all. Bright field imaging is different. This half mode imaging that I have also discussed. So here from this, if you will know, or if you will change the your zonal axis selection, then you can get from here. See, this is for the different axis, but for the same family, like 111. So zonal axis selection is also very important. Intensity in SAT pattern is related to what? Wavelength of electron beam, camera constant, Bragg's diffraction condition, structure factor. So this I will show you. I don't know whether you know or not. So structure factor, it is related to the intensity of the diffracted beam. Why it is popping? Okay, yeah. So I think it's 8 also. So yeah, I will just quickly give you this. So the structure factor will be the answer. So here it is somewhere related to the intensity of the diffracted beam. So here in this slide you will get in a much detail, because here when you will use a type of a plane in a crystal, that will have which will have a different spacing and the different intensity of atoms, and so you can expect the intensity of electron diffraction that will be different for the each atomic plane. Okay, so by changing the structure factor, the intensity of diffracted beam will also change. So intensity in SAT pattern is related to your structure
Boss,
factor.
it is correlated with the electron wavelength also. No? If the electron beam wavelength is lesser, then you can go for the higher intensity beam.
But here since for the one material, if you are using, you need to fix your the wavelength of your electron. You can't
Yes, yes.
change.
Okay, okay,
So it's
understand.
not like you are changing. Suppose if you are doing experiment, you can't change in between your wavelength of the electron. You need to keep
Understand.
constant that.
If lambda is not
Ha-
constant, then
Yeah.
we can difficult to correlate the d spacing as well.
Yes. So just by the structure factor, intensity of this you can control in the SAD pattern. So I hope that's all for today, that I have collected the question. So I believe that maybe if you are finding some difficulty in this lecture, then just go through the book which I have suggested for the WD Callister, for the introduction to the material science. There you will get some information regarding the Berger vector, dislocations, and some basics regarding your crystallographic, and whatever you want, you can get there. And if you want some more details, then let me know. I can also suggest you some standard books for the different specific different topics. But I hope that this assignments you will be able to solve some questions, not some, more than the 60 to 70% which I have discussed from the today's lectures, I believe. So which is related to this. So does anybody having or have some question which they wanted to ask, some technical question?
It's not non-technical. The lectures are related to IIT Kharagpur. Okay, Shubhankar Rai. Now you are from
Yes.
IIT Bombay. How you are correlating? Are you working with him or something?
Okay, so since it is not technical, let me stop the recording. Just